The universe, in its most fundamental form, operates on principles that often defy our everyday intuition. At the heart of this subatomic realm lies quantum mechanics, a theory that has revolutionized our understanding of matter and energy. Central to this theory are quantum numbers, a set of discrete values that dictate the properties and behavior of subatomic particles, most notably electrons. Much like an address defines a location, quantum numbers provide a unique set of coordinates that pinpoint the state of an electron within an atom. Imagine an atom as a bustling city, with electrons zipping around like tiny cars. Just as traffic rules govern the flow of vehicles, quantum numbers impose specific restrictions on the movement and interactions of electrons. These rules dictate where electrons can reside, their energy levels, and how they interact with other particles. Without these quantum regulations, the atomic world would descend into chaos, devoid of the order and predictability that governs the formation of molecules, and, by extension, all matter. The discovery of quantum numbers marked a pivotal moment in our scientific understanding. In the quantum world, where particles like electrons exhibit both wave-like and particle-like behavior, classical physics falls short. We need a new set of rules, a new language to describe the subatomic realm. This is where quantum numbers come into play. These numbers are not mere labels, they are quantized, meaning they can only take on specific discrete values, much like the steps on a staircase. Each quantum number corresponds to a specific physical property of an electron, such as its energy or angular momentum. These numbers are crucial for understanding the behavior of atoms and molecules. They dictate how electrons arrange themselves within an atom, influencing the atom's chemical properties, how it interacts with light, and its magnetic behavior. The principal quantum number, denoted by the letter N, is akin to an electron's energy level within an atom. It's like the floors in a building, with each floor representing a different energy level. The higher the floor, the greater the energy. Similarly, the larger the value of N, the higher the energy level of the electron. So, an electron with N equals sign 1 occupies the ground state, the lowest energy level, while an electron with N equals sign 2 resides in the first excited state, and so on. This number can take on any positive integer value, such as 1, 2, 3, and so on, with no upper limit. This means there's an infinite number of possible energy levels for an electron, but the energy difference between levels decreases as it increases. Think of it as the floors in a skyscraper being closer together the higher you go. The principal quantum number also dictates the size of an electron's orbital, the region of space where an electron is most likely to be found. While the principal quantum number defines the energy level of an electron, the Azimuthal quantum number, denoted by the letter L, reveals the shape of an electron's orbital. Imagine each energy level as a floor in our atomic building. Now, each floor is further divided into rooms, with each room representing a different subshell, characterized by its unique shape. The Azimuthal quantum number determines the type of room or subshell an electron can occupy within a given energy level. The value of L depends on the value of N. For a given N, L can take on integer values ranging from 0 to N1. So, for an equal sign 1, L can only be 0, meaning there's only one type of subshell on the first energy level. For an equal sign 2, L can be 0 or 1, indicating two different subshells, and so on. These subshells are often represented by letters: S for L equals sign 0, P for L equals sign 1, D for L equals sign 2, and F for L equals sign 3. As we delve deeper into the quantum realm, the magnetic quantum number, denoted by ML, comes into play. If we continue with our building analogy, where each floor represents an energy level and each room a subshell, the magnetic quantum number specifies the orientation of an electron's orbital within a given subshell. In essence, it tells us which way a particular room or orbital is facing. For a given subshell, the magnetic quantum number, ML, can take on integer values ranging from L to plus L, including 0. So for L equals 0, S subshell, ML can only be 0, meaning there's only one possible orientation for an S orbital. However, for L equals 1, P subshell, ML can be -1, 0, or +1, indicating three different orientations for P orbitals, often designated as Px, Pi, and P. The final piece in our quantum number puzzle is the spin quantum number. denoted by ms. This quantum number describes an intrinsic property of electrons known as spin angular momentum, often simply called spin. Unlike the previous three quantum numbers which arise from the electron's motion and position within the atom, spin is an inherent property of the electron, like its charge or mass. Imagine an electron not just as a point particle orbiting the nucleus, but also as a tiny spinning sphere. This spin, however, is purely quantum mechanical and doesn't have a direct classical analog. It's not that the electron is physically spinning like a top, but rather that it possesses an intrinsic angular momentum, which is quantized and can only take on two possible values. The periodic table, a cornerstone of chemistry, might seem like a simple arrangement of elements, but its underlying structure is intricately linked to the quantum world, governed by the rules dictated by quantum numbers. The periodic table's arrangement, with its periods and groups, is a direct manifestation of the principles of quantum numbers, reflecting the electronic configurations of elements. The principal quantum number, n, dictates the period number of an element. Elements in the same period have their valence electrons, the outermost electrons involved in chemical bonding, in the same energy level. As we move down a group, the principal quantum number increases, signifying that the valence electrons occupy higher energy levels, leading to larger atomic radii and different chemical properties. Within a period, the elements are arranged in increasing order of their atomic number, which corresponds to the number of protons in the nucleus. Spectroscopy, the study of how matter interacts with electromagnetic radiation, provides a powerful tool for probing the structure of atoms and molecules. By analyzing the wavelengths of light absorbed or emitted by a substance, we can gain invaluable information about its composition and the energy levels of its constituent electrons. Quantum numbers play a pivotal role in interpreting and understanding these spectral signatures. When an atom absorbs a photon of light, an electron can transition to a higher energy level, but only if the photon's energy matches the energy difference between the two levels. This energy difference is dictated by the principal quantum number, n, and the Azimuthal quantum number, L, which define the allowed energy levels within an atom. Consequently, each element exhibits a unique absorption spectrum, a fingerprint that reveals its identity. Emission spectroscopy, on the other hand, involves analyzing the light emitted by an atom when its electrons transition from higher to lower energy levels. Again, the wavelengths of emitted light are determined by the energy differences between levels, governed by the quantum numbers. Chemical bonding, the force that holds atoms together to form molecules, is fundamentally governed by the behavior of electrons, and as we've seen, electron behavior is dictated by quantum numbers. The formation of chemical bonds hinges on the interactions between the valence electrons of participating atoms, and it is the quantum numbers that determine the energies, shapes, and orientations of these valence electron orbitals. Covalent bonds, where atoms share electrons, arise from the overlapping of atomic orbitals. The shape of these orbitals, determined by the Azimuthal quantum number, L, dictates how effectively they overlap, influencing the strength and directionality of the bond. For instance, the dumbbell-shaped p orbitals overlap in a head-on fashion to form strong sigma bonds, while their sideways overlap results in weaker pi bonds. In ionic bonds, electrons are transferred from one atom to another, resulting in the formation of charged ions. The tendency of an atom to lose or gain electrons, and hence its ionic character, is determined by its ionization energy and electron affinity, both of which are influenced by the atom's electronic configuration and the quantum numbers of its valence electrons. Quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels, relies heavily on the concept of quantum numbers. These numbers are not just arbitrary labels, but fundamental properties of quantum systems, defining the quantized states of particles like electrons, and determining their allowed energies, angular momenta, and other observables. The Schrödinger equation, the central equation in quantum mechanics, describes the wave function of a particle, a mathematical function that contains all the information about the particle's state. The solutions to this equation are a set of allowed states, each characterized by a unique set of quantum numbers. These numbers, therefore, are not merely descriptive but are directly obtained from the fundamental equations of quantum mechanics. Furthermore, the Heisenberg uncertainty principle, one of the cornerstones of quantum mechanics, states that certain pairs of physical properties, like position and momentum, cannot be known simultaneously with arbitrary precision. From the structure of atoms to the behavior of molecules, from the colors of fireworks to the operation of lasers, quantum numbers permeate the fabric of our physical world. They are the keys that unlock the secrets of the quantum realm, providing a framework to understand the intricate dance of electrons within atoms and the forces that govern the formation of matter. These numbers, arising from the fundamental principles of quantum mechanics, are not mere abstract concepts confined to textbooks and research labs. They have profound implications for our understanding of the universe and have led to groundbreaking advancements in science and technology. From medical imaging to telecommunications, from renewable energy to quantum computing, the impact of quantum numbers on our lives is undeniable. As we continue to explore the quantum realm, unraveling the mysteries of the subatomic world, quantum numbers will continue to serve as our guideposts. They will illuminate the path towards a deeper understanding of the universe and empower us to harness the power of the quantum world to address some of the most pressing challenges facing humanity.